actually. I can move even closer. Let's come over here. There we go. And it's recorded. Okay. We're going to look at Chapter 6, Chemical Reactions. Come on. There we go. All right, so what's the evidence for a chemical reaction? Just imagine yourself in a dirty medieval alchemist's cubbyhole. How does this person know that something's going on? Well, they probably look for visual signs. You might see a color change. You might see gas, evolution of gas. You might see a change of phase. That's not necessarily a chemical reaction, but that's an indicator. And then in worst case scenarios, it might blow up in your face. But those are visual cues. There are other sensory cues also, such as you can sense some heat maybe coming off of the reaction, or it might get colder. Or you may even hear something. So along with a visual signal of gas, you might hear some sizzling. So some of the indicators that a chemical reaction changes, color change, solid forms. Usually, if the temperature does not change and a solid forms, that's a good bet you have a chemical reaction. But if a solid forms and it's not a chemical reaction, the temperature has to change a lot to change the phase. Gases form, heat, or maybe even a flame is a possibility. So here's an example of a chemical reaction. Drop a 9-volt battery into a glass of water. And if it comes out of the tap, it's probably got enough ions in it, it'll conduct electricity and go ahead and do that. Or you can put a couple of drops of vinegar in there and it'll make it conductive. Then the battery will split the water into oxygen and hydrogen. So the clue there is evolution of gas, right? Bubbles present. How about this one? In this case, we're adding something to the flask, and the color is changing. Right? In this case, you have hydrochloric acid is coming out of this pipette, and it's entering this solution of cobalt nitrate. Cobalt nitrate in aqueous solution is going to be a pink, or if it's concentrated enough, it'll be reddish. But if you add the hydrochloric acid to it, the chloride in the hydrochloric acid is going to replace the nitrate. And then you get cobalt 2 chloride. And cobalt 2 chloride is blue. So you get that color change as an indicator of chemical change. And we use chemical change, color changes like that all the time in a procedure called titration, where you add a known amount of a certain chemical to one and you wait for a color change. When the color change, you stop. And then you measure the volume of what you delivered. And you can use that information to quantify what's in the flask. It's called titration. In this one, we're adding one liquid into another one, and you're getting a solid form, actually a yellow solid. So we have a solution of sodium dichromate, and we're adding it to lead nitrate. So this is the dichromate solution, and the dichromate gives it that yellowish orangish tinge, but the lead nitrate is colorless. But they're both solutions. So when you add them together, you get a reaction, and it forms a solid, a yellow solid. Actually, it takes the dichromate, combines it with the lead, and the lead dichromate is insoluble. So a chemical reaction there. So in this case, we have a reaction where methane is the gas delivered to your house by the pipeline, is primarily methane. And then you light your stove, and it takes oxygen from the air and burns it, produces carbon dioxide and water, plus a lot of heat. I mean, that's the whole purpose of doing it. But that is a chemical reaction. When a chemical reaction occurs, we don't create matter, we don't destroy matter, we just rearrange the atoms. That's all there is to it. So if the equation is balanced, you'll have the same number of carbons on this side as you do on that side. In this case, we do. 4 hydrogens on this side, 2 hydrogens on that side. So that equation is not balanced. We're not accounting for 2 of the hydrogens. Right? So we're going to develop a procedure for balancing equations. And the equation itself is written in such a way that the reactants are on the left-hand side, products are on the right-hand side, and the reaction, if there's only one arrow with a barb pointing to the right, of course, the reactants go to the products that direction. Later on, you may see reactions which have double barbed arrows. So you have an arrow barbed the other direction, and that just means that the reaction is reversible. It can go back the other direction. But typically, we write the reactants on the left, products on the right. Okay. Check something. Okay. Oops. What happened? There. I'll just pound this topic really hard. In a chemical reaction, we don't create, we don't destroy matter. We only rearrange the atoms. Now, energy may be produced, it may give off heat, or it may absorb heat in the process. But that's a different topic. The atoms are still there. If we have a reaction where we're using polyatomic ions, such as the dichromates earlier, that's a polyatomic ion, and in a reaction, oftentimes the polyatomic ion stays whole as a reactant and product. In that reaction we showed you where the solid, the yellow solid, was formed, it did maintain its integrity. So in those cases, you can treat these as a single unit because it's the same here and the same there. Recognizing, of course, that the atoms themselves have not been created or destroyed, but for reaction budgeting processes, you can treat the polyatomics as one unit. Okay, so when we balance this equation, before we had the equation looked like that. If we count our atoms, we find that we have this many here and there and there. Then once the equation is balanced, we need, let's go back to the hydrogens. 4 hydrogens here, we need 4 there. So how do we get 4 hydrogens? Well, we got 4 hydrogens by having 2 waters rather than 1 water on this side. And we had, and in that case, we've also unbalanced the oxygens. So we got 4 oxygens on this side. Now we need 4 oxygens on that side. So we need 2 waters on this, 2 oxygen molecules on the reactant side. When we do that, then we have 1 carbon, 4 hydrogens, 4 oxygens. 1 carbon, 4 oxygens, 4 hydrogens. Now we're balanced. And the way we write the equation, once you have the compound written correctly, here, 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 there, or the element, then you can't touch the subscripts. They're sacred. The only way you can balance the equation is with these numbers in front, the coefficients. You can change those all day long if you want.
May I go? I need to go to the doctor. Is that going to be able to invite for it?
Yes, I'm sure I'm recording at this time.
Is it all right? You sure? Is it okay if I go?
Yeah, sure. You got a doctor's appointment or you're so sick you got to see the doctor, go ahead. Okay, so when we write these equations, oftentimes it's important to include the physical state of the reactants and products, especially if we think we might be producing a solid, like we did with the dichromate, the lead dichromate. So we would indicate just to the other side right here, we put a little S there in parentheses, which means it's a solid. For liquids, say we had liquid water, and we were going to make drop our 9-volt battery in there and make the gases. Well, to be balanced, of course, we need to do that. Now we're balanced. But these are indicators of the phase. The only one that's not a pure phase is AQ. We put the AQ next to a reactant or product when it is in aqueous solution, right? Which means if you want to deal with it, you got to know its concentration. There are other symbols that could be used, but these are the most common ones and the only ones that we're going to use in this course. So if we have, in this case, we've got solid potassium metal, and that will be in a mineral oil. Keep it in mineral oil because it's very reactive with water. So any water from the atmosphere, it'll suck that water right out of the atmosphere and react with it. Because, and here you have liquid water, and if you put this in that, you get that. A violent reaction. You produce hydrogen gas and potassium hydroxide in solution, and you produce so much heat that it's sufficient to ignite that hydrogen as it comes out and combines with the oxygen in the air. Very exothermic, we say. So if we, in this reaction, we're saying in words first that if we shine a blue light on a mixture of hydrogen and chlorine gas, those elements will react and produce hydrochloric acid. Actually, They say gaseous hydrochloric acid. If HCl is a gas, we call it hydrogen chloride. It's only when you dissolve it in water that you call it hydrochloric acid. So the authors that created this slide are a bit off their rockers. So what's the unbalanced equation? Well, you have to write the reactants, right? So we got hydrogen gas, and remember, hydrogen gas is always diatomic, and chlorine gas, which is also diatomic. And the product is hydrogen chloride gas. Okay, so they're all gases. But to balance it, we've got 2 of these and 2 of those, but only 1 over here. So if we just put a 2 in front, that gives us 2 hydrogens, 2 chlorines, and these coefficients always propagate through the entire molecule, right? So 2 times 1 and 2 times 1 gives you 2 of each. So that's the unbalanced equation, right? We wrote that first. And then I just went the extra step and balanced it. Okay. So I already said that. In most cases, the reactants and products have to be experimentally determined. You can't just put reactants here and say, oh yeah, they're going to make that. Because if the conditions vary widely enough, you might get a different set of products from the same reactants. There are some cases, like that reaction where we combined dichromate and the lead in solution, that, yeah, when you put those together, they're always going to give you that yellow precipitate. So for those, you can predict the outcome. But in most cases, you have to be told what the products are. And then you deal with that in terms of writing the correct compound and then balancing the equation. Okay, so this is just in words, how you write a balanced equation. You have to pick out of the problem, what are the reactants, what are the products, what are their states. You have to write the formulas correctly. So if we tell you sodium hydroxide, you know it's got sodium, and hydroxide is a polyatomic ion, right? Then you have to see, is the equation balanced? So sodium is going to be a +1, and you look up your hydroxyl in the table, and it's -1, so yeah, 1 to 1, that's fine. It's written correctly. Then you write the unbalanced equation. Once you've got the unbalanced equation, then you proceed to the next step, which is balancing the equation. Now, the authors of most chemistry books tell you that when you balance your equation, they call it balance by inspection, which is a cop-out because it doesn't give you any instructions as to how to proceed the most efficient way to balance an equation. I'm going to do that. In fact, let me be sure it's here. In your review document, does it have? Yes. In your review document on page 46, I have helpful hints for balancing equations. Okay? So those are used in combination with my budgeting process that I'll show you. But before we get to that, if we have the same number of atoms on both sides, then the equation is technically balanced. But we want to be the most efficient, and we use the smallest whole number values that we can get. So while 2, 2, and 4 would be valid, it's not the best. Right? So the best is 1, 1, and 2. That's the preferred. There are circumstances, I'll just add this as a comment. There are circumstances where fractional coefficients are used. There's special cases, and they're used for a very special reason. But for now and for the foreseeable future, use the smallest whole number ratios. So here we have an equation. Right? It's a solid. We're going to combine it with oxygen, gas, and it's going to make 1, 2, 3 solid. Okay. Just for practice, let's name these things. This one, oxygen's always 2 minus, so that makes this 2 plus. So this will be iron 2 oxide. Right? That's oxygen gas. How about this one? That's always 2 minus, so we have 6 minus. We need 6 plus over here, that means this is 3 plus. So this one would be iron 3 oxide, otherwise known as rust. Okay, that's not part of the problem about the question here, but I thought it's a good teaching moment. Okay, so how do we balance that? Well, the way I've developed over the years is to set up a budgeting process. It keeps you from getting lost. It makes each move the most efficient. So out here to the left, I put the elements that are part of the equation. Iron and oxygen are the only 2. Right? So then you say, what are you starting with? Well, on this side, you're starting with 1 and 3 oxygens, 1 here, 2 there, right? On this side, you're ending up with 2 irons and 3 oxygens. Okay, so that's your starting point. Then, when you get a chance to look at those helpful hints, you'll see that one of them is, if you've got an element by itself on either side, leave that one till last. The reason you leave it to last is because if you put a coefficient here, it only changes that element. It doesn't change anything else, right? So you're not messing with any other element. So we save this one till last. And as it turns out, the oxygen's already balanced. But I suspect that once we balance the irons, we're going to mess with the oxygens. Okay? So if we've got 2 irons on that side and 1 iron on this side, then we'll make 2 irons on this side, like that. But then that will make 4 oxygens for it. Right, 2 and 2 is 4. Okay, so now we have to deal with the oxygens. So how do you make these 2 balance one another? And the next trick is to use a fractional coefficient as an intermediate step. Right? So an intermediate step would say, all right, so we need to reduce this side by 1 oxygen, right? We want to make this 3 instead of 4. So how do we do that? Well, we've got 1 here, which gives us 2 oxygens. Let's just take a half of it. And if you take a half of that, that only gives you 1 oxygen plus 2 is 3. So now technically it's balanced. Well, I picked a bad one, first one, didn't it? So now that we have 2, half, and 1, the way to get rid of that fraction is you just multiply the entire thing through by 2. It gets rid of the half. Right. So now this one becomes 4. This one becomes 1. And this one becomes 2. So now after all that mess, we had it balanced right here. Right? It was balanced with a fractional coefficient. So if you multiply the entire thing through by a number, a whole number, then it's still balanced. So you don't have to go back and check. So let's write it the way it's balanced now. 4 FeO, right, plus 1 oxygen yields 2 Fe2O3. And you can go check yourself to be sure. 4 oxygens plus 2 is 6. 2 times 3 is 6. 2 times 2 is 4 irons. 4 irons. So it's balanced. Okay. So that budgeting process is the slickest way to get to the answer without fumbling around. Some of the more complicated reactions can be started at different points, right? One is more efficient than the other, but just because you started somewhere else doesn't mean you won't get to the answer. It just takes you a few more steps. But one thing that you got to watch out for, if you don't write these, say it's a word problem, if you don't write these correctly, you'll never balance it. So if you go through 12, 13, 14 steps and it's not balanced, go back and look at your compounds to be sure they're written correctly. Oh, oftentimes a question, exam question will say, what's the sum of the coefficients? You know, that just makes it easier to write multiple choice questions. So that would be 4 plus 1 is 5, 6, 7. So there's, and when we do this sum as a question, we're looking at the simplest whole number ratio. Right? So if you had 8, 2, and 4, technically that would be right, but it would give you the wrong answer because you put 14 instead of 7. Right? Okay, so it's important for the purpose, test-taking purposes, to get the simplest whole number ratio as your answer before you do that calculation. Okay? We have a few more minutes. Let's proceed. Okay, so this slide just kind of hammers home the simplest whole number ratio. So if you look at these choices, rather than go through all of that, look at these choices and say, all right, so let's eliminate the ones that cannot possibly be. All right, let's look at the compounds. Are these written correctly? Calcium is 2 plus, oxygen is 2 minus, that's correct. Carbon, that's probably graphite, and it's a simple element, that's fine. This one is calcium is 2 plus, and carbon would have to be 1 minus. Let's see, is that possible? Let's look at our table. Oops, how'd that get in there? Oops. So let's look at the periodic table. Carbon. And it's probably not right. But I can't say that it's not right, because every one of our choices is CaC2. So it's possible. Let's look at the others. This calcium oxide is wrong. Oxygen is always 2 minus. So that can't be. The rest of them, possibly. That's okay. Those are consistent. Those are consistent. Now, what are the others we can eliminate? Anything that's got a fraction in it. Eliminate that one. Right? So then we look at these two. So what's the simplest whole number ratio? Well, this 4, 10, 4, and 2 can be divided by 2, right? So by process of elimination, that one's out, and this is your best answer. Then, if you've got time, you can go in and say, all right, 2 calciums, 2 calciums, 2 oxygens, 2 oxygens, 5 carbons. It's 4 carbons plus 1 is 5. So it's balanced. Technically, that one is too. But this would be an intermediate step, right? If we used this procedure, it could possibly be an intermediate step. And then you just multiply through by 2 and get rid of the half fraction. Okay. So the preferred one is that one. Okay, which one of these is, these true-false questions can kind of trip you up, but you have to use a little logic and say, all right, is that even possible? Subscripts and the reactants must be conserved in the products. No. The only thing that determines the subscript is the formula for the compound. Right? So you write the compound according to its balanced formula before you even start to balance the equation. So the subscripts are not conserved. Coefficients are used to balance the atoms on both sides. Yes. That's the only way you can balance is by adding that number in front of each compound or element. So this one's false. And that's probably the only one that's false. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. And that speaks to the getting rid of a fraction, for instance. Right. The key to a chemical reaction is that to recognize that you're talking about numbers of atoms, moles of atoms. And the ratio of those in the reaction is the key. Once you've established a balanced equation, that ratio is constant. It will not change. So if you multiply your coefficient on one side, you multiply the rest of them by the same number. Phases are often shown for each compound, but are not critical to balancing the equation. That's true. You don't have to know the phase to balance an equation. Once you've got your compounds or elements written correctly in reactants and products, then it's just number shuffling. Doesn't matter what the phase is. So the only false one is the first one. Okay. So what do we mean by stoichiometry? Stoichiometry is what you do with your equation after it's balanced. A balanced equation will tell you the relationships among the reactants and products, and you can use that to determine how much product you'll end up with if you start off with a certain amount of reactant. Do that, which is typically the way it's used most often. You can also determine, well, maybe this product, this reactant runs out and we got some left over from this other product. Like one is limiting and the other one is excess. That is quite typical of a reaction. But that's stoichiometry. You have to go through the steps, okay? You got to, when you read the problem, you got to see what are the reactants, what are the products. Then you got to write them correctly, right? Is it an element or is it a compound? Write them correctly, put them in their proper position on either side of the arrow. Then you can move to balancing using our budgeting process. Only once you've got a balanced equation, only then can you do stoichiometry. Right? So it's a the steps are limited. Following steps are limited by the previous ones. You can't get to the next step until this is done properly. If you mess up any one of those steps and you're on your way to stoichiometry, it'll never happen. It won't work. Okay. So that's chapter 6, and we'll look at chapter 7, which is reactions in aqueous solution. Now, let me see. Most of this one is going to be balancing equations. I think so. And then when we get to chapter, we've already done chapter 8. So we're going to move to chapter 9 next. Syllabus. Let me get a feel for where we're headed. Okay. So after we've done all this balancing stuff and looked at solution chemistry, then we'll work on quantities. So that'll be for these two are on the next exam, and then the quantities will be followed. They'll probably be close to spring break by then, won't it? It's creeping up on us. Yeah. Okay, so I'll put this up on Blackboard just as soon as